Hello there, it's Mr. Smith with the video on rates of change, and I'm very excited about this video because we're going to jump right into calculus and see where you apply it and when you apply it and how you can use calculus to estimate how things change in our world. So let's take a look. The structure of this video, we're going to have an introduction with some definitions that you'll want to get down on your notes. And then we've got a few examples to lead us through how we might estimate rates of change, distinguishing between average rates of change and instantaneous rates of change. So let's dive right in here. There are two different types of rates of change we're going to talk about. The first one is what's called average rate of change. You may have seen this before in a previous class, but basically it's our slope. And it's slope between 2 points that are on a function. We say that's f of b minus f of a over b minus a. In other words, change in y over change in x. The great thing about calculus, as we're going to discover over the course of this year, is that when we apply the limit to an average rate of change, it becomes an instantaneous rate of change. Hopefully at some point you've thought about traveling in a car, for example. And if you travel 120 miles in 2 hours, we would say that we travel 60 miles per hour. That's like an average rate of change. But when the interval that we use to calculate our speed traveled gets smaller with the time, like for example, instead of measuring over 2 hours, you measure over 2 minutes, you get closer and closer to what we call an instantaneous rate of change. And that's the limit part right here. The limit is really telling us that we're making b and a be values that get closer and closer to each other. And when those values get closer and closer to each other, then we're going to end up with what happens at an instant, the rate of change in particular. You're going to see this in a couple of examples, but basically we're going to use average rate of change, which sometimes we call AROC, to approximate instantaneous rate of change, which we call IROC, using either a left method, so that's approximating using some sort of value that's at A, and a value to the left of A. And you'll see an example in just a minute, so don't worry. We've got the right method, a value at A and a value to the right of A. And then what we call the straddle method, which uses values that are close to A on either side of A. And all of these methods can be used to help approximate instantaneous rate of change. And spoiler alert, if we know a function, we're going to actually be able to create a function which tells us our instantaneous rate of change. That function is what we call the derivative. So early in the year, we're talking about this idea that is so fundamental to calculus, and this is the idea of the derivative. The derivative is going to be some sort of a function that's going to tell us the instantaneous rate of change of the function at x is equal to a. All right. The derivative is going to be so crucial to what we do going forward because this idea of change is something that we're studying in calculus. There are 3 different notations you'll see pretty frequently. In fact, 2 really that you'll see most of the time when you're dealing with derivatives. Just to introduce you to some of this notation, maybe the most frequent one we use is what we call the Lagrange notation. And this is pronounced f prime of x. All right. And what f prime is it's going to be a function which tells us our instantaneous rate of change at any one moment. Sometimes you'll see it as y prime. If your function is g, you would see g prime. And this little apostrophe is what the prime part is. You might even see Leibniz notation. If y is a function of x, you'd see this written as dy dx. This is the one maybe that makes more sense. Maybe you remember in some sort of class where you learned about slope, you learned about how slope can be written as delta y over delta x. Well, the Greek letter delta is just a d, and that's how we get dy over dx like this. That also represents a derivative or an instantaneous rate of change. A notation that's used maybe more in physics, but not so much in calculus is this y with a dot over it. That's Newton's notation. And we'll talk all about the story behind this later on. If x is the independent variable and y is the dependent variable, like y equals f of x, when we talk about a derivative, we'll say we're taking the derivative of y with respect to x. Okay, the respect to x means that we're respecting our independent variable. I can't even begin to tell you how many applications there are. You're going to be seeing so many. So for example, the derivative or rate of change of a position function, the rate of change of your movement is velocity. And the derivative or rate of change of your velocity is acceleration. That's just one example. We're going to spend a good deal of time talking about how position, velocity, and acceleration all relate to each other. For now, let's do some simpler examples. Let's say we'll consider y equals x squared plus 1. And we want to find the average rate of change of y with respect to x over the interval 3 to 4.5. How much does y change with respect to x? Well, if you think that this is just like slope, you're right, it is. All we're going to do is find out what our change in our function is and divide it by our change in x. And in this case, we would plug 3 and 4.5 into our function to get our change in y on the top here. And by the way, yes, I will be looking to see that you set up things properly. That means showing me this, what we call difference quotient, to determine what your average rate of change is. So you do need to show your work. I went ahead and plugged in 4.5 and 3, and I calculate it, and I get my average rate of change as 7.5. You're just finding the slope between 2 points on this function. It seems a little weird because slope is a linear thing, but what we're doing is leading up to this idea that, well, maybe most functions that we look at can actually be described by a line. All right, consider y equals x squared plus 1. Use one of the methods named previously to approximate the instantaneous rate of change of y at x is equal to 4. All right, so we have 3 possible methods we can use. We can use what's called the left method. And what we're going to do is we're going to use an average rate of change for numbers that are near 4 to approximate our average rate of change. So here I plug in 4, and then I use a number a little to the left of 4, 3.99. You could even get closer if you wanted to. So I did all the calculations and found an average rate of change of 7.99. We can use the right method. In this case, we use x is equal to 4.01 and x is equal to 4. So we use the value itself and a value that's a little bit higher than 4. When we plug those values in and we calculate it, we get 8.01. So notice these are pretty close to each other. If we use what's called the straddle method, we would use a value a little bit lower and a little bit higher than 4. So I use 4.01 and 3.99 and plug those into my average rate of change formula. Calculate them by plugging in our values for x into our function, and we get 8. So notice that's right in between the two of them. Maybe not always the case, but it is here. Luckily, your calculator also has a way to do this, so let me show you that really quickly. If you have a TI-84, you're going to be helped out here. Otherwise, I'll have to show you in class how to do this. So one of the ways you can go about doing this is plug your function y equals x squared plus 1 into your calculator. And if you go to math, number 8, you'll see this thing called nderiv. All right, I'll be calling it math 8 from now on. Your input will look a little something like this. You want the derivative with respect to x, so you type a little x in there. And let's introduce you to this idea of vars. I have my function plugged in under y1. So if I go to vars and yvars, under function, it'll let me just type in y1 without having to retype the function. So this is going to find the derivative of y1 at x for x is equal to 4. And when I plug that in, math number 8 gives me the answer of 8. That's the exact answer actually for what the rate of change is, instantaneous rate of change is at x is equal to 4. You surprised that we're going to be able to actually find the actual instantaneous rate of change? It's going to be interesting. All right, example 2. The graph below represents a position curve for the height of a ball and measured in feet over time measured in seconds. When is the instantaneous velocity 0? So imagine a ball that's been thrown up into the air. It goes up and then it falls back down. When do you think the instantaneous velocity is 0? If you said that's time 1, you're correct. In this case, we have our instantaneous velocity at time 1 when the ball starts to change direction. And you'll notice I drew a little line right there at the peak. All right, there's going to be something relating to this line and the slope of this line in particular that's going to relate to the fact that the velocity is equal to 0. Later on, we'll talk more about that. Okay, example 2, the graph below represents a position curve for the height of a ball. We want to estimate the velocity of the ball at time t equal to 0.5, given that the position at time 0.4 is 10.24, at time 0.5 is 12, and at time 0.6 is 13.44. So I tried to get 0.5 right about here. So basically we're trying to find the slope of this line right here, what we're going to call a tangent line. Well, how do we estimate the velocity? How do we estimate the change in position over time? Well, we could use the left method. I could use 0.5 and 0.4. It's not completely accurate, but it gives us a good idea of what's going on. All right, so I use my values of 12 and 10.24, and I calculate my average rate of change with values that are close to each other. That makes it an estimate of the instantaneous rate of change. So here we get 17.6. Or I can use a right method. I'm going to use 0.6 and 0.5. So here the height was 13.44 at 0.6 and 12 at 0.5, and I get 14.4 feet per second. Or I can use what we call the straddle method, right? Use the values on either side of 0.5. And when I do so, I get 13.44 minus 10.24 over 0.2, which is 16 feet per second. So all these give us an estimate of what our instantaneous rate of change is, or our velocity. Finally, example 3, suppose we have a table that describes f of x. Selected values are given in the table below, and we want to find the average rate of change on the interval 2.560 to 3.500. Show your work. All right, this is all about just knowing the formula. It's our change in f over change in x, just like slope. So I find my function at 3.500, which is negative 0.351. I find our function at 2.560, which is 0.549, and divide by my change in x, and I get negative 0.957. You definitely have your calculator for something like this. All right, selected values are given in the table below. We want to use the chart to approximate the instantaneous rate of change at x is equal to 3. How do you think you would do it? We have 3 methods: left, right, straddle. Well, the table doesn't give us much choice because we don't have values at 3, so we're going to have to use values that are close to 3 using what's called the straddle method. So by the way, remember that original formula. What we're finding is the limit as x goes to 3 of f of x minus f of 3 over x minus 3. There's a guided practice question about that. This turns out to be what we call f prime of 3. That's the derivative at 3. And to approximate it, notice I'm using my approximation symbol. That's also big here. We would do f of 3.004, a little to the right, minus f of 2.980, a little to the left. Notice those are the closest values we can choose to x is equal to 3, divided by 3.004 minus 2.980. And we calculate that, and we get negative 1 when we plug in our values. So in summary, an average rate of change, or AROC, is calculated with points close to each other, would give us an approximation for what we call instantaneous rate of change, or IROC. So it's basically the slope for 2 points that are close to each other on a function. Be a key concept. And we can use graphs, tables, and equations to find our AROC and IROC. Thank you very much, and we'll see you in class.